Well, thank you, everyone. Thank you, Donna, for giving me this opportunity, and thank you to Kin Mining for allowing me to present results that have all come about in the last 6 months. Not quite true. The exciting results have come in the last 6 months. In the beginning, I got a question in February last year. Do we have VMS mineralisation in our drill data? And the answer, just looking at the geochemistry, is resoundingly yes. And that is because if you get a metric which has a lovely positive association with that wide suite of pathfinder elements, and there's more besides, the answer is yes. Now, we're not getting VMS ore grades, well, 1.3 copper if you had enough of it, but these are the best values out of thousands of 48 element analyses. But it's got a good, strong sniff. And looking at the top 10, we've got a really robust, so I've coloured up, obviously in red, really anomalous. Just to give you a reference, ACA is the average crustal abundance. So the anomalies kick in at about 10 times average crustal abundance. And what you can see is that for many of the samples, it's giving you consistent anomalism in that wide suite, particularly diagnostic things like tin, selenium, when we're trying to differentiate this from orogenic gold. We'll get to that. Some of this is weathered. So where you're seeing that the zinc is missing, you'll see that the sulfur is lower and the cadmium is also down. So we need to be mindful of what's fresh and what's weathered. When I started this work with Kin, they owned all of this, but they have since sold the core part of the gold resources to Genesis. So today, after making this very presentation to Kin, I had to put an exclusion. That's the tenure that's been sold to Genesis. But what we see, we've got the top 10 over on the left, which are the squares. But as we go down through the threshold, there's the vague suggestion that we're getting some stratigraphic control on this anomalism. A later product, when I returned, we'll see this later in the talk, how that map was made, but the red and the pink is highlighting the VMS anomalous geochemistry, whereas the green and the orange, they're the gold deposits. And we needed an index which could differentiate the two, and we'll get to that later. So then the next question was, September, I was asked, is the Welcome Well formation VMS prospective? I said, get some samples and we'll analyze them for the full periodic table, including rare earths, and we'll be able to tell whether they have a permissive geochemistry. And then in November went and mapped it, because the answer was yes. So there's two things in my book that really say whether VMS is prospective. The first of those, I don't know if you can read from the back, but where that pink and green trace, where these dive down, niobium tantalum, that's a negative anomaly. And that's typical of subduction-related volcanism in the modern arcs. God knows what it meant back in the Yilgarn. But what is universal is that if you get into a VMS belt, you will always find volcanic rocks with that feature. And the other thing you'll find is a flat, heavy rare earth profile. Now, I won't go into all of the details, but what it tells you is that that melt was shallow. If it's a deep melt like a porphyry copper, the amphibole and garnet will hold on to the heavy rare earths, and they'll do it progressively. So you'll get a slope rather than a flat profile. Shallow melting, very high heat flow. You have to have it for a VMS environment. So yes, and I've made this box in iogas. If the heavy rare earths are too steep on the x-axis, it's not prospective. And then your mid-ocean ridge basalt with that flat profile, that's not prospective either. But we have those, and that's the important thing. It doesn't all have to be prospective. You just need some. And the mid-ocean ridge basalt could even be the host of the VMS mineralisation. And this is the trouble with consultants. I went from February doing that work. I went on to something else in June. And then when I came back in November, I'd forgotten what I'd done in February. However, Villiers-Journa, who's not here, is the geologist who was helping me with the mapping. And he'd logged a hole in 2002. And that hole was analysed just for gold. It's a geochemist stream. But in his log, he'd put VMS, because he's looking for gold. He's got 2 years experience. Sphalerite is known as the gay deceiver. It's not shiny and metallic like the other sulfides, but he saw something different and he remembered it. So his question to me was, do you want to look at this hole I logged in 2022? I said, yeah, sure. And then when I got there, I went, holy shit. This massive sphalerite is the first VMS mineralisation discovered anywhere in this whole belt. If you go onto Mindex, I meant to make this slide, there's not a base metal occurrence in over 50 kilometres strike of rock. And now we've got this, and that's the excitement of this. I think there was a complaint about this being a bit promotional, but it's very exciting science as well. And I think that's why we come to these talks. So yeah. That's from that hole, IP 22 DD001. Got assayed, of course. We don't have gold only anymore. So you'll have seen the announcement if you've gone looking for it. The headline was 6.7 metres at 5 zinc with some copper and so on. The important thing to note is that you don't really see that because I've just showed you the best parts of it. Most of the intersection is not massive. So it's really some portion at around 20% zinc and the rest is gangue, really. But you can see some very important things here. That is that the copper really kicks in the lower half. So you've got that classic zinc at the top, copper at the bottom. Deeper down in the footwall, so now we're 20 metres lower down, we get some really chloritic rock with chalcopyrite and pyrite in it. Not a lot of chalcopyrite, it's only 406, but it's a lot higher than the surrounding rocks. So then we look at magnesium and we say, well, the blue one's up the top, that's really mafic rock. That's the sort of magnesium you'd expect in a rock like that. But immediately underneath the massive sulfide at 280 metres and 290 metres, we've got 4 and 5% magnesium in rocks that should not have that much, and that's your chloride alteration. And just remember the blue, the pink and the green coding. This is what we found in the mapping, and this is what we found in the drill hole. So I've done them different colours for some silly reason, but the mid-ocean ridge basalt, which we largely sampled from, well, all of it was dolerite down in the deeper footwall. But now we're starting to get basalts and shallow dolerite sills up in the drill hole. So that's that magma series, the morb. The pink and the green on the left are really the same thing. The green is just a bit contaminated, and we'll get to what the rock looks like. It's not volcanic, it's a conglomerate. It's almost a monomic conglomerate, but where we were getting contamination with other clasts, the green was just a bit steeper. So we can really condense the stuff on the left to one magma series. The new kid in town is that much steeper niobium tantalum anomaly. We don't need to worry why. All it's telling us is that the 10 metres of strata that host the VMS mineralisation is something new. So it's largely chert and carbonate, but it's also got presumably some volcaniclastic with a felsic signature. And this is going to be one of the keys, I would hope, I will push for, is that we map with our eyes, our hammer and our hand lens, but we augment that with this style of trace element geochemistry to correlate different units around the project, be they intrusive, clastic, whatever. So making that point again, thorium niobium is a very good XY plot to separate the different magma series. In the drill hole, they also happen to be single compositions, but outside of the drill hole, we're going to get a variety of compositions for each magma series. Our metal geochemistry, so this is abundance relative to basalt, which is very similar to abundance relative to average crust. And what that's showing is that you have 10, 100, 1,000 times enrichment in this wide suite of elements. And that's why, as a geochemist, I'm prepared to say from the office, that's a VMS, because nothing else does that. We've got a plot here, calcium versus magnesium. Perhaps that's a trend towards dolomite. So when I say silica carbonate, it's probably silica dolomite. But we see some samples heading off towards the chlorite node, and they're the chlorite altered samples. A very widely used diagram where we've got sodium over aluminium versus potassium over aluminium. The cool thing about this diagram is that we can plot some very important alteration minerals, and we're seeing that chloride alteration trend as well as the sericide alteration trend from what we would expect as least altered compositions. So there's an awful lot in that data from hole 1. So now let's go back to the drill database. And so I've changed the cutoff. And what you can see now, more clearly, that red line is a very pronounced break in arsenic and the weighted sum that we get from the surface geochemistry. But you can also see that that geochemistry is following along that break. So I would interpret that as very important, all that anomalism along that trend. And when we go out and follow that trend mapping, we're finding gossans. So it's working well. And I'll get to explaining what that weighted sum, how that works in a minute. This is the one where I'm not just solely looking for VMS, I'm trying to discriminate the two. So I'm just adding the log of indium, tin, cadmium, and selenium. And I chose those elements because they don't play any part in the orogenic gold. So if they're high, it's due to VMS on this project. Have another project, you want to differentiate other styles of mineralization, you're going to have to come up with a different index. I'm going to subtract gold, moly, and tungsten. Now, gold and moly are part of the VMS Pathfinder suite, but they feature far more heavily in our orogenic gold mineralization. So if I add up 4, subtract 3, I can very comfortably make that map that we saw earlier. And now we really clearly are seeing these linear zones, which when we put on the geology map are following stratigraphy. And when we go and have a look in detail, we're finding chert horizons. To show how effective that discrimination is, I've got a split probability plot. Now, who needs an explanation of how probability plots work? One. All right, well, I'm going to do it all for you. They're like histograms, but they're way better, okay? The 0 score is the 50th percentile, the median value. And each of these populations, if you just had a simple probability plot, there'd be just one trace for one population. And the 0 score is the median. And then we just have a normal distribution. So from -1 to +1 standard deviation, 68% of the data are in here. And you can see how it thins out towards the tails. That's because there's less and less the further away you go. And that corresponds to the bell curve of a normal distribution. It's just a really effective way of displaying different populations and seeing what's going on. And so what we can see is that the pink in particular, because that's the strong VMS mineralization, I've highlighted with indium at the -1 score. Now, below -1, there's only 16% of the data, okay? The same amount of indium is over +1. That means that the orogenic gold that has more indium is less than 16% of the data. So that one element is pretty good at discriminating the two. But when we throw in tin, selenium, cadmium, which also have strong discriminating power, we're not going to be getting any VMS mineralisation, orogenic gold mineralisation, other than where we've got mixed. And we do see that in the chips, in the core. Well, the core is really the only place you can see it clearly, is orogenic gold overprinting VMS mineralisation. And those cherts are great hosts for orogenic mineralisation. They bust. Oh, whereas particularly gold, but to a lesser extent, tungsten and moly are the ones that favour the strong orogenic gold in green. So that's the basis. Now, I'll zip through this. This is similar to Scott Halley style, pulling apart different compositions. Now, I'm giving it an igneous name. A lot of the time it's a sedimentary rock. All we're doing here is really chemostratigraphy until we map these rocks properly. That's interesting, that pink one right up the top. Looks like that's a synucleotoid signature, which is a tick for the gold prospectivity of this area. And then we've got all sorts of other profiles, but problem is we don't have the full rare earth element suite. And we rarely have ytterbium, lutetium, and some of the other elements. So it's a bit of a half job. So we need to do the full job now to define this stratigraphy properly. And here we see just the felsic units that are different. So that one there is an example of not prospective. It's got that steep profile falling away, whereas others are flatter, but you don't have nearly enough of the heavy rare earth elements to tell that properly. Anyway, this is a combination of geography and geochemistry. And what that's done is allowed us to put different stratigraphic units, geochemical stratigraphic units on the map. That needs basically redoing with the full rare earth element data. Okay, surface samples. Drive me nuts. If you ever do more than gold on surface samples, you must include iron and manganese. If you do not include iron and manganese, you cannot correct for iron and manganese scavenging. You go and follow the highest copper values, well, good luck. So it's a bugger. I don't have all the elements I want. I don't have iron and manganese to level it, but it still worked quite well. So we've used an 8-element index, and that's what you can see there. So the thing I'll really point out, where that red arrow comes in, shows the enrichment horizon. Everything north of that is just dead. And that's the Welcome Well formation. No VMS mineralisation in that at all. And you can see that even more clearly with antimony. I should have made smaller blue dots. If we get in closer, now we can see that the surface anomalism is looking quite similar to the drill. So I'm going to toggle this backwards and forwards. So that's the drilling and that's the surface. So some of them, yes, some of them, no. But that means, you know, if the drill anomaly is under some transported overburden, they're not going to match. If the drilling hasn't hit exactly what you want, but there's a pretty good correspondence in this VMS anomalism, both at surface and at depth. Right. So now what I've been doing is, I'll call it surveying the cherts. It's not mapping. All I want is to know in detail where it goes and get a sample every 50 metres. So these are the first results of that. The black trace is IP001, and it turns out that the best cherts are a bit to the south of that. So the way I would interpret that is that it could be thrusts, but it doesn't look like it. They look like separate chert units without thrusts. And if that's so, if we're looking at a stratigraphic section there facing to the west, I would say that you've had a discharge zone underneath the first chert, more strata on top, new seafloor, new VMS event, more strata, and that's classic around the world. You see that in a number of places. But what I'm hoping for is that we get nice long stretches of black and then some anomalies, and initially that's working well. We went and revisited the anomalies, and the chert is nice and pyritic. So it looks like it's working well. So I've gone and made a map just by logged sulfide. So we still don't have geochemical results, but where we do have both, I'll toggle again, you can see that that bright patch in the middle is where we've got logged sulfide. So the relationship isn't perfect, but it does suggest that sulfide is a reasonable predictor of getting that VMS anomalous geochemistry. And this time I've got the full suite of elements, 12 elements. It's going to be extremely robust at pulling apart the wheat from the chaff. So there it is. I only got 74 samples, but when you get such a close agreement, so you could say, well, which elements are actually the best? Which one correlate with that log indice the best? It's things like selenium and indium. Gold's the worst. But what's really interesting about gold, I've put that orange line there at 0.1 grams per tonne, and I've studiously tried to avoid any orogenic veining. And I'm perplexed, to say the least, as to why the chert horizons should be so rich in gold. Now, if it's gold by virtue of VMS, why aren't all the other pathfinders there? I don't know, but you know, that goes up to 7-8 grams per tonne of gold, and other than some disseminated pyrite, there's nothing to explain it. Okay, a whole lot of favourable horizons. I've been losing a bit of sleep that, you know, if you have too many, you might just spread your metal budget over too many favourable horizons. So I had a look at the Noranda camp. I haven't put the total there, but I think it's 260 million tonnes of ore, dominated by the Horn deposits, which together are pretty well 200 of those million tonnes. But there's some nice prizes, and in that 5 down to 1 million tonne range, some really good high copper grades. And first look at the map, you'd think, geez, it'd be hard to put all of them on one horizon. Well, we're going to zero in on an area from those 3 green circles down to the red circle, and a schematic section where there are multiple, they're interpreted as exolites, so they're cherty, pyritic sediments, and with these deposits along them. So there's certainly precedence in multiple horizons yielding a good result. In terms of, is there enough room to fit a district? So I've got the scale here, the same as the cartoon on the other side. There's abundant room within this volcanic belt to fit a serious VMS district. What I have to point out, though, is the VMS district is smaller than the whole volcanic belt. So what's being outlined here is in the pink dot cartoon, is the subsection of that volcanic belt. But the point is that there's room in there plenty to fit that. This is the samarium neodymium isotope. So all I'm going to point out here is that if the model age pretty well matches the igneous age that we've measured from zircons, then that's a primitive volcanic. And what that means is it's come straight from the mantle and spewed out and done its business. Most magmas in the Yilgarn derived from, at the very least, some enriched mantle, but mostly they've had long crustal residence times, and that's why they have much older model ages, because the samarium and neodymium have had plenty of time to evolve at a faster rate than things would at the mantle. So what we're looking for is a match. And what we see here is that blue trough has model ages pretty much the same age as the volcanic rocks in the eastern goldfields. Although it's a different colour, the Golden Grove trend is pretty close to the 3 million year age. And within the Yilgarn, they're pretty well the only nice prospective areas. What I've put that brown dotted outline around is the failed systems where you don't even have a resource, but process happened, but it wasn't nearly good enough because we weren't working with that direct connection from mantle to full volcanic stratigraphy. But Golden Grove and Teutonic Bore sit in or close to, and so these tenements, again, are situated in much the right place. People make so many analogies between the Yilgarn and the Abitibi, but this is the big difference, and I would say why they have such a rich VMS endowment. Sorry that the colours are reversed, but now it's the hot colours that have model ages very close to the volcanic ages. So there's the Abitibi, which is just one of a number of areas of pretty well wall-to-wall primitive crust. So in the Yilgarn, we're going to need to be a lot more selective than take your pick. So we had our session today at Kin about targeting. These are good if you can find them. So that's a siliceous gossan on the right. We're going to have a look at that more closely. The photo of the ferruginous gossan isn't quite good enough to see them, but there's beautiful squares after pyrite cubes in that hematitic black ironstone. And the one up in the top left is coarser pyrite than you would commonly see, but coarser pyrite in the chert. So that's what these anomalous cherts can look like. But what I want to do is just flick. Here we're seeing a bit closer up. And again, I'm just going to flick forward and then toggle backwards. I'm just pointing out those areas where there look to be what we call boxworks, nice cubes after pyrite. Because you can get a web work just like that, except for the cubes, out of just siliceous residue on top of a dolomite. So there are plenty of false siliceous gossans. We don't have assays for this one yet. I think SEPA got up to Carl's Folly 9. So I hope that this one has all the metal in it of a VMS gossan, but it looks right. And Bruce Hooper in the audience seconded my diagnosis. Here's another gossan where it's bloody clear. You can see no problem, the squares in that one. And another example, it didn't even put it on the map, but I was following the chert horizon, and then there's this silkrete. And where we had that beautiful siliceous gossan, most of it doesn't look like that. A lot of it is just massive, ugly silkrete. So perhaps even massive silkretes can be VMS gossans. And I've certainly seen at Sulphur Springs, you've got the beautiful honeycomb stuff, but you've also got big slugs of snot that is just massive pale brown silica. So who knows? But it's lovely to be in the Yilgarn in 2024 and still be in the game to find gossans at surface. It, begs a lot of questions. I'm still scratching my head. Beautiful columnar jointing. I put this one on LinkedIn because I've never seen quartz veining filling up the joints. And we're just going to go now for a rampage through the various volcanic textures, because understanding volcanology is one of the most important things to pulling apart a VMS district. We log so much by codes, but who records contacts? And the contacts here, be they volcanic, sedimentary, pepperitic, magma mingling, on and on it goes. And we're going to have a look at some examples of those. And we need to know these relationships to be able to predict where the VMS is going to fit into that volcanic architecture. So I was talking about the Welcome Well formation, that it's not volcanic. Well, it's the first cousin of volcanic rock. You've got all of these andesitic cobbles in a sandy andesitic matrix. But here we've got one of the ring-ins, a felsic clast with a completely different geochemistry, and that's what pulled that green profile slightly away from the pink one and was sort of pushing it out of the perspective box. the bulk of the rock is perfectly prospective, and then occasional clasts are very, very not prospective. So that's what we're dealing with down at the base. Here we've got a different type of breccia. This is a hyaloclastite breccia. I haven't put in a picture of pillows. Oh, no, we will do that in drill core. This is if the pillow basalt formation goes into overdrive and you start getting lava fountains. It was Jocelyn McPhee that first showed us this at Sulphur Springs, but for my personal experience. So what you've got there are basaltic blobs with chilled margins that have settled into glassy debris. So we can't map that as a conglomerate. We can't map that as a tectonic breccia or all these other things that we need to be able to correctly interpret. And the key to interpreting any breccia, I would say, is what's the matrix? And its relationship to the class rims. Pepperite. We've got a wacky and black shale down sequence and a dacite above. So it's that beautiful mixing zone between wet sediment and magma. We need to be able to differentiate that from the first two examples. And we haven't yet found a large volume of felsic coherent volcanic, lots of volcanoclastic, but VMS deposits very, very commonly form where you get that felsic volcanic center. So mapping these things out, and the pepperite counts as the edge of a coherent block or coherent unit of felsic volcanic. So that's going to be one of the very next jobs, is to map out where do we have coherent felsic volcanism, because the cherts above those may well be particularly prospective. Nigel, this is the one, Nathan, sorry, that I was telling you about. We might have to have a look later, but this is this concentric silica into wacky. Problem with calling this a pepperite, as I found out on LinkedIn, is that the clasts don't have chilled margins and they're much too coarse. So how the hell you get a doleritic lot of fragments into wacky like that? You can tell me afterwards, Nathan. So there's certainly some mysteries there. The one above is just showing working left to right at the top, basalt, a small zone of semi-massive sulfide, tiny bit of chert, some more basalt, then a break, then the bit of core poking out the end of the tray, small massive sulfide, chert, basalt, chert. What I'm getting at is that's a key horizon, and it's important to us that that's mid-ocean ridge basalt footwall, in the middle, and hanging wall. So we've got a new horizon that we haven't seen anywhere else yet. The next three photos are just pepperites working our way down the core. So one, quite angular, two, less angular, and then getting really fluidy as you get into more and more sediment. I wanted to cut a particular piece of pillow basalt just to see the flat surface, and when it fell open, I thought, oh, gecko. So that's particularly pretty, but yes, two examples of pillow basalt in core, and then some more pepperites because they're so much fun. This has got me stumped. This is a polymic breccia, but in the polymic breccia are some nice coherent units of dolerite and basalt. And on the left, where those three yellow crosses are dolerite apophyses of something completely different into the polymic breccia. I have no idea what that is, but I would love an expert to come and have a look with their hand lens to tell me that I'm not smoking too much. And you can see there that on the right-hand side, the yellow nipple poking off the basalt out into this polymic conglomerate. So really strange things going on, and we need to be able to work out what all of those are and what they mean to the location of VMS deposits. Here we've got something different, bulbous, fluidy, a coarser grained mafic magma with a finer grained mafic magma. I'm going to call that magma mingling. And I'm very much looking forward to a critique of my interpretation of all these textures from the experts, but that's what I've made of them. And the best way to learn you're wrong is to stand up and tell people about it. That is a doleritic matrix to this polymit conglomerate. This, again, does my head in. That's what it looked like to me under the hand lens, and that's the best photo I can give you. One of our favourable horizons, the chert. So this beautiful laminated silica, not much carbonate in this one, with pyritic bands. There's several pyritic bands, but you can only see one of them clearly. And again, timing relationships really matter. So I've zeroed in on where this black band cuts across, and it looks like it cuts. Oh, sorry, it looks like the pyrite cuts that later feature, in which case it couldn't be sedimentary pyrite. But when you get in really close with your hand lens, what you see, if you go down one layer, you can see the mid-grey layer is cut by the black cross-cutting vein, but it doesn't obliterate it completely. It's not a vein, it's an alteration zone. So when you get in with your hand lens, you see that the pyrite is the one thing that the black later vein didn't obliterate. So what I'm saying is when we get to cross-cutting relationships and interpreting the relative timing of that pyrite, we've got to be really careful, because at first glance, it looks like it's being that the pyrite cuts the later black vein, but I don't think it does. I shouldn't say vein, alteration zone. Important sedimentary textures. Well, this was just, these are the andesitic volcanoclastics, so tuffs. So beautiful flames, graded bedding, and cross bedding and so on to give us the stratigraphic way up. And I was really banging the drum. It's not just enough to observe these. It's not just enough to digitally enter the holes into Leapfrog. I'm convinced that if a geologist spends 1 hour reviewing what they've logged, which could have taken will have taken a lot longer, and draw one of these, two things will happen. They'll see a whole lot more that they didn't see the first time, but it will consolidate in their head in a way that they won't forget nearly as easily as to what it all means. We can get the codes, we can shove them in the computer, but just the exercise of putting pen on paper and drawing that, because I haven't done it much in the past myself, but I certainly knew about it. And that was certainly my experience. I saw a whole lot more, and it brought together the whole meaning of what we drilled through. So I think if we do this, as I hope we do, that will be part of it. So to the conclusions, it's very early days, but we do know that we've got the right fertile VMS lithogeochemistry with the Welcome Well, and that there's a zone where we're getting a younger, well, it's not younger, is it? It's, well, you have much of the Welcome Well is older, then you have this coeval interleaving, and then the succeeding morb ultramafic is the Maneri formation. It's the VMS mineralisation looks at this stage to be in that sandwich of interleaving of the two formations. The metal signature that we see, it's in surface sampling, drill samples, and the massive sulfide is the classic VMS signature. So you've got the commodity elements with a kitchen sink of Pathfinder elements. Well, this is the interpretation that it's VMS smoke, but I can't quite see how you're going to get all those elements spread out so beautifully stratigraphically without shear zones or veins to explain it. Fallout of black smoker dust explains very neatly why we've got that VMS metal signature on not one, but several favourable horizons. And when we go and look at them, it's that hiatus in seafloor activity. It's a chert. It's not in the middle of a dolerite or in pillow basalts. It's always that hiatus, quiet water sedimentation. And so I would say multi-element geochemistry, mapping, structure, volcanology in particular, alteration, they're all working. So at this early stage, a lot further to go. And then, of course, the IP, the downhole EM, hyperspectral, all these sort of things to come will be the way that I hope we approach this. Exciting opportunity. We'll see what happens.